we're not going to panic if we don't see that up in the top because I have to move around between screens today. Wow, everybody's here. How cool is that, man? That is awesome. So all of the lectures that anybody may have missed are all up on the portal, and you can get them from there if you need help. If you've made arrangements with me to make things up this week, I need you to do that. Interim grades are due on Thursday, and it would be nice to be able to include everything for everybody. It feels quick, but I think it's just because we had the 2 weeks off in the middle. Okay, so we're working on section 6.2. We talked last class about sigma notation, and I'm going to have to do this because it's just out of control. Oh, God bless America. All right, well, you know what? I guess that's just going to be the way it is then. I'm going to be writing 3 inches below where I am. So we talked about how this works and that this was sigma notation. And that this symbol here merely told you that you were going to be adding everything up. This was the thing you were going to add up. And then K was that index that told us what we were going to run between. So remember, this was going to be A1 plus A2 plus dot, 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 plus AN. Okay, and we did a whole example. Oh man, we did a whole example where we talked about how it kind of matters what the index is depending on what you're doing. God, this is ridiculous. I can't believe this. And see, it won't let me do any of those other things from here. Well, let me do it from here. That key won't even work. I'm trying to rectify the board, which is when I press the little buttons, but you have to press both of these at once. But for some reason, it's not accepting the keyboard key, so it won't read both. It'll only read one of them. So every time I write, I'm like a centimeter below, except up here where it's even more because of the way the screen works. So it's really annoying, is the bottom line. And I have to be able to draw things specifically, and I'm not going to be able to do that. And I think the problem is that the keyboard key isn't working, because there should be a keyboard that pops up, and nothing's happening. And I don't know how else to make that happen. All right. Okay, so we are going to talk specifically about Riemann sums. Which take LRAM, MRAM, and RRAM from that RAM program a whole step farther. So we're going to consider a continuous function that's defined on some closed interval from A to B. And just like we did with RAM, we're going to divide this function into subintervals, n subintervals. By choosing n minus 1 points between A and B. Okay. So if I wanted to have 5 subintervals, I'm going to pick 4 points, right? Because then A to the first point would be my first interval, first to second point would be my second, second to third would be my third, third to fourth would be my fourth, and fourth to B would be my fifth. Right? Got it? Okay, then I'm going to pick those 4 points in the middle, and I'm going to end up with 5 subintervals. So when I do that, I'm going to let x0 equal A and xn equal B, so that P, which is a set that's going to be equal to x0, x1, x2, x dot dot dot, xn, is the partition of my interval AB. Okay. Bless you. Okay, so if I go back up to my graph and I pick all my points, this one's going to be x0. I'm going to let this be x1. I'm going to let this be x2. I'm going to let this be x3, and I'm going to let this over here be x4. They don't have to be evenly spaced. Okay? Those are kind of evenly spaced, which I regret. And then, go ahead. Yes. Good call. Okay, or in this case, 5. For the example that we're playing with here. Okay. So each of my subintervals has a width delta xk that's equal to xk minus xk minus 1. Which might look a little weird, but just hold on for a minute and we'll write down an example or two. Okay. What? It's those points that I use to make the edges of my subintervals. Yeah. Okay. Yup. Xk minus 1. The next thing I write down will probably make it make more sense. Okay. So for example, x1 is going to be x1, because that's what the k is, minus x times 1 minus 0, 1 minus 1, which is 0. So the width of my first subinterval is the difference between x1 and x0. Casey? Yes. It's very hard for me to write because the board's screwed up. So delta x2 is going to be x2 minus x1. Okay, does that make a little more sense? Okay. And then, just to make things even more exciting, within each subinterval, I'm going to select a number ck. It's another stepping stone. You will probably be asked, on the AP exam, you may very well be asked to do a Riemann sum. However, when we actually get there, it's probably going to look different than what we're doing right now. Okay, so what these CKs are, if we go back to our graph, okay, is it's just a point within each interval that I'm going to use in a minute to make the height of my rectangle. Okay, so I'm going to make them green just because I need a color. So this might be, let's make sure I've got my subscripts right. This may be C1. This, which would be really crazy, is C2. This is C3. This might be C4. And over here might be C5. They don't have to be in the middle. Well, because they're x values, yes, they should be on the x-axis, except that I can't make the frickin' board do what I want it to do. Okay. So then what I'm going to do is I'm going to use f of ck, okay? So the height of my graph at each of those ck values for the height of my rectangle. Okay, so if I go back to my graph, let's see if we keep it low, if it'll help. So this is going to be f of C1, right? This is going to be f of C2. This is going to be f of C3. That's going to be f of C4. And that's going to be f of C5. And then I use those values to make my rectangles. So remember, the width of my rectangle goes from x to x value. So there would be one. Here would be another one. Here would be another one. Here would be another one. And here would be another one. Okay. And this width here, for instance, is delta x1. This distance here is delta x 1, 2, 3, 4. Okay. So it's really what the Riemann sum is doing is giving you a defined way to use RAM. Okay, it's giving you a definition, a system, a way to choose the values that you need to choose to do basically summing up the rectangles. Except why you would ever make your rectangles not be the same size, why you would ever choose a value for C that wasn't right smack dab in the middle of the interval, I don't know. But it has to be a generalized thing. Okay, so everybody got their picture? Okay, so then we say that the Riemann sum for f, which is the function, on the closed interval AB is the sum of the area of these rectangles. So my Riemann sum, which is going to be Sn, is going to be my summation as I go from k equals 1 to n for however many subintervals I have. F of ck, remember that's the height of my rectangle, times the width of my rectangle, which is delta xk. And as we saw when we were playing around with the RAM program on your calculator last week, is that the more subintervals you make, the bigger an n value you have, the more accurately your sum reflects the area under the curve. You don't have as many gaps where the curve goes over the rectangle. You don't have as many places where the rectangle extends out from underneath the curve. So you're not underestimating, you're not overestimating, you're able to fit it in better. Okay? You with me? All right. So RAM was this program that we used without really talking about how we used it. Riemann sums is the math, is the calculus behind that program. Okay? With a few simplifications. So, definition number 1. I'm not going to leave this up here for a very long time because you should have already written this into your journal, so I don't expect you to copy it down. The definite integral as a, is that what I want? Definition 1, yeah. The definite integral as a limit of Riemann sums. So let f be a function defined on a closed interval AB, like the one we just had, for any partition P of AB, so that's however many values of x I choose to break my function into, or my interval into. Let the number ck, those were those values we picked to be the height, be chosen arbitrarily in the subintervals x sub k minus 1 to k. You know what that means, okay? That was this, all right, that I'm just picking these random values that I'm going to use to find the height of my rectangle. If there exists a number I such that as the width of my longest subinterval goes to 0, this sum, which is just the height times the width of my rectangle, becomes that letter I, no matter how the P's and the CK's are chosen. Then we say that f is integrable on AB, and I is the definite integral of f over AB. Okay, this tells us that no matter how we partition the function, if the limit exists, then f of x is integrable. Not everything in our lives will be integrable. And the definite integral over AB is this letter I. There will be things you cannot take the integral of. We'll find that there are things that you cannot take the integral of because you will get something ridiculous. This is one of those things. what has an antiderivative that's the natural log of x? No, that's the derivative of the natural log of x. If I told you to take the integral of 1 over x dx, then that would be the natural log of x plus c. The markers are dead again. But, okay, so there will be things that we won't be able to take the integral of. Okay? So theorem 1 is the existence of definite integrals. And it tells you that all continuous functions are integrable. That is, if a function f is continuous on an interval ab, then its definite integral over ab exists. Okay? And if you think about it, it kind of makes sense. Again, you have that written in your journals. So if I can make any continuous function, and I take sub-interval here, can you find the area under the curve in here between A and B? Technically, yes. Okay. If instead my function looks like this, and here's A at the origin, and here's B out here, are you going to be able to find the integral of that? No. And actually, that's a continuous function too, but it's got a problem. So there will be problems. But what if I had something like this, where there was an asymptote here, and I wanted you to find the area from A to B? Yeah. Okay. What? I believe it is. And we will talk about these and how to deal with them later on. It never ends, and that's part of the problem. But we will deal with those later, okay? So when we look at the definite integral of a continuous function on AB, what we're doing is taking the limit as n goes to infinity. What's n again? The number of subintervals. So if I take an infinite number of subintervals, each of which will be infinitesimally small, and you know how much I love to say that word. So if I add all these up, and again, remember that f of ck is just the height of my rectangle, and delta x is going to be the width of my rectangle. But to make my life a little easier, I'm going to make all my intervals have the same width. So I'm going to let delta x be b minus a, which is the length of my whole interval, divided by the number of subintervals. So there's no longer a little k down here because all of my subintervals are going to have the same width. Okay. Now, if you were in AP Physics last week, we talked about this a little bit when we talked about taking or finding the center of mass of a continuous object. That when I was finding the center of mass of a continuous object, I had an infinite number of pieces that I had to add up. And I told you, and I'm telling you again now, that if I add up an infinite number of pieces, right? Because I'm letting my number of subintervals go to infinity. When I add up an infinite number of pieces, that sum becomes, with a drum roll, an integral. So that sum is going to become the integral from a to b of f of x dx. As I let n go to infinity. See, and I can't even fix my infinity because of the stupid board. Okay. And let's talk about what all these things are called. So we're going to start with the squiggly thing there, which is the integral sign. And the integral sign, as we've talked, is an operator. It's an instruction. It is actually a key on your calculator. You will, in fact, be able to take definite integrals on your calculator. But it's not a number in and of itself, it's an action. It's an alert. Okay. A is the lower limit of integration. And it's also the lower limit of the interval. And B, you might guess, is the upper limit of integration. F of x is what is called the integrand, or the function that we're integrating. And then dx, which is like a bookend with our integral symbol, tells us that x is our variable of integration. So you read this as, because it's important when you go off and you're sitting in a calculus class and a professor points at you and tells you to read a problem, that you feel confident that you can do it. Okay? So this is the integral from a to b of f of x dx. Or you might say the integral from a to b of f of x with respect to x. Okay, but that's how you read it. Now, the book talks a little bit about dummy variables. I don't know, do they use that word? Do they use the word dummy variables? Okay. What it basically means is my integral from a to b of f of x dx is equal to my integral from a to b of f of y dy is equal to my integral from a to b of f of w dw is equal to my integral from a to b of f of smiley face d smiley face. Okay? It doesn't matter when you're doing a definite integral what the variable is inside the integral. As long as f is a function of the same symbol that you're integrating over. So as long as this and this are the same symbol, I can express that function any way I want and it doesn't matter. Okay, because we call the f or the y or the w or the smiley face a dummy variable. It's just hanging out so you have something to write down and substitute into. It's a placeholder. Okay? All right? And that will come back later, where we will write our function in terms of a different variable. And you need to remember that, oh, wait a minute, Dr. Goetz said that was okay. That as long as whatever my variable in x and whatever comes after my d are the same, it doesn't matter what it says. Okay? All right, so I would just like to do, real quick, page 286, number 1. Just because it puts together what we've been talking about. And then when we come back tomorrow, we'll continue with and hopefully finish 6.2. So what do the instructions tell us? Sarah, you have your book open. Would you read it? Summation k equals 1 to n, and then what? Okay. So we're supposed to make this look like an integral. And remember, the fact that I'm adding up, which is the summation part, an infinite number of things, that becomes an integral. That's what an integral means, is that I have an infinite number of subintervals and I'm adding up the contribution from each one. I'm adding up the area of each rectangle. Okay. This is my function. This is my f of ck. So how do you think I'm going to write that? Nope, it does not also include delta x. Because remember, f of x is the height of my rectangle. It tells me where that ck value is going to put me on the curve, and it tells me that distance I'm going to be from the x-axis. The delta x just tells me how wide my rectangle is. So what's ck squared going to become? It's my function. And so instead of being f of ck, somebody say it? Not ck squared, but x squared. Okay, because I'm not picking individual ck's anymore. I'm going to use every x value that I have because I have an infinite number of subintervals. Okay. The delta x tells me that x is my variable of integration. So that's going to become my dx. And one thing that I didn't give Sarah a chance to read was the interval, which goes from 0 to 2. And these are going to be my upper and lower limits of integration. So that sum becomes the integral from 0 to 2 of x squared dx. All right. We got it? We're going to make it? Okay. So we'll pick up here tomorrow and do some other things. If you had trouble with exploration 1, you might want to look at that again because we're going to talk about it tomorrow. I've got a little more to do. If you have journal questions tomorrow, we can talk about those as well. Okay?